Hi everyone, this is our first video for Chem 1041, our Friday lecture on May 16th, 2014. So the first thing that I'd like you to do is you can pause this video and go get a piece of paper and a writing utensil for the quiz. Okay, so first we'll start with the slide that we left up on Wednesday. Here we're talking about temperature and molecular speed. So as the temperature increases, we have more molecules that are moving faster. And when they go fast enough, they have enough kinetic energy that they can overcome the intermolecular forces that keep those molecules close to each other in the liquid, and they'll actually go into the gas phase shown here. So the thing that's keeping these particles close to one another are the intermolecular forces. Okay, so I'd actually like to ask you your first quiz question, which is related to what we talked about on Wednesday. I'll repeat the question twice. Question 1 is, how much heat in kilojoules is needed to convert 866 grams of ice at negative 10 degrees Celsius to steam at 126 degrees Celsius? Again, how much heat in kilojoules is needed to convert 866 grams of ice at negative 10 degrees Celsius to steam at 126 degrees Celsius? So in order to get full points for this question, you need to show all of your work. Might be helpful to draw a diagram like we did the other day. Okay, let's move on. So we talked a little bit about vapor pressure and how vapor pressure is the pressure exerted by the vapor on the liquid. So it's right at that gas and liquid interface. So as the vapor pressure increases as the temperature increases, and vapor pressure decreases as the strength of intermolecular forces increases. So if you think about the intermolecular forces are the things that keep those particles, those molecules, close to one another. And so when those intermolecular forces are stronger, things are going to want to stay, say, in the liquid phase instead of go to the gas phase. So that means that there's not going to be as much in the gas phase. So that means that it's going to lower the vapor pressure. So this is just an example here of a graph that shows the vapor pressure versus temperature of a couple of different compounds. Okay, so now let's talk about vapor pressure and boiling point. So we know the regular boiling point of water is 100 degrees Celsius, but it actually can change based on the external pressure. So if we think about boiling water for pasta, the external pressure is the pressure that's in your kitchen. So the temperature at which your vapor pressure equals that external pressure of the room or the surroundings is the temperature at which the liquid will boil. So it will actually change based on the weather. We can't really observe this change very much because usually the external pressure only varies slightly. So for your second quiz question, I'd like you to actually pause the video and go to a weather website, and I'd like you to write down the name of the website, the date, the time, the current temperature, and the current pressure. Now the pressure might be in kind of a weird unit. It's usually in inches of mercury. And we'll talk about that on Monday, why they use different units. So that's quiz question 2. Okay, so now let's talk about the normal boiling point. So usually we talk about things at standard atmospheric pressure and temperature and things like that. It just makes it a little bit easier when we're doing calculations, and it kind of gives you a basis to compare to. So the normal boiling point is the temperature at which the vapor pressure is equal to standard atmospheric pressure. So that is 760 torr, or 1 atmosphere, or 101 kPa, which is kilopascals. So as the boiling point increases, as the external pressure on a liquid increases. Okay, so like before, we talked a lot about the qualitative aspects first. So things like vapor pressure increases as temperature increases, a little bit more conceptual. So now we'll go into quantifying things like the effect of temperature. And this is using the Clausius-Clapeyron equation. So that is shown right here. So ln, if you forgot, is natural log. And the way to get rid of natural log, if you're doing an equation, e to the natural log of x equals x. So to get rid of the natural log on this side, you would say e to the natural log of p equals e to this whole power, and then you would just get p equals e to this whole power. So another thing to note is that R is the gas constant. So that's 8.314 joules per mole K. So if you notice the figure on the right here, they're straight lines. And if we think about how to represent a straight line, it's y equals mx plus b. So we can actually relate the Clausius-Clapeyron equation to a straight line. So if we know two different temperatures or two different pressures, we can calculate the other one using the Clausius-Clapeyron equation. So here you can see we have P2 over P1, and we have T2 minus T1. So you should be able to recognize this equation and be able to do calculations such as this and this. I think there's one on the homework as well. So now for question 3 of the quiz. I'll repeat it twice. What is the delta H of vaporization of a liquid that has a vapor pressure of 621 torr at 85.2 degrees Celsius and a boiling point of 95.6 degrees Celsius at 1 atmosphere? So I'll say that again. What is the delta H vaporization of a liquid that has a vapor pressure of 621 torr at 85.2 degrees Celsius and a boiling point of 95.6 degrees Celsius at 1 atmosphere? So you're free to pause the video and work on that, or you can work on these questions after you watch the videos. Okay, let's move on to phase diagrams. So this is a phase diagram for CO2. If you remember, we were talking about dry ice. And the sublimation and deposition, so sublimation going from solid to gas, that happens right along this line at various pressures and temperatures. So things you should know about the phase diagram is 1, the triple point and what that means, and the critical point and what that means. And then also recognize this is where the supercritical fluid is. And we talked about that a little bit, kind of being one of those fourth phases. So the next phase diagram is for water. So here one of the things you'll notice is that the solid-liquid line slants to the left for water. So for question 4 for your quiz, why does this slant to the left for water? You can just give me a couple sentence answer for that one. Okay, so before we do the summary, I have another question. Question 5. If substance A has a higher vapor pressure than substance B, which one has the higher boiling point? I'll say that again. If substance A has a higher vapor pressure than substance B, which has the higher boiling point? Okay, so at this point, I'd like you to take a few minutes and write out a summary or draw pictures or something like that for section 12.2, and just try to recall as much information as you can about what we learned about. You can also refer to your notes. So this will conclude video 1 for our lecture. I've divided it up into 3 videos, one for each section, to make it a little bit easier, so you can do them at your own pace. So now you can take some time to do those questions and then open up video 2.